All right, so what's going on there? He puts glass into that solution, completely vanishes. Now you can't see it. It's a magic trick of some sort, or at least it looks like a magic trick. Glass is there, you're not able to see it. So the question is, why not? Why is it that you're not able to see the glass? You're going to be able to feel it, but you won't be able to see it until he pulls it out. So how does the magic happen?
Since the dawn of time, people have looked to the sky and seen omens and miracles in the extraordinary lights and colors. Rainbows were seen as bridges to the world of the gods, sun halos as the headgear of angels, and mirages as glimmering cities in the distance. But with our modern scientific understanding, can they all be explained through known principles? As light passes through the Earth's atmosphere, it is affected by changes in temperatures, as well as particles in the air. Contrary to our common understanding, sunlight does not always travel in straight lines. It bends, bounces, and refracts, creating a host of dramatic atmospheric optical effects. Everything our eye perceives is in one way or another a trick of the light. For example, if the sun gives off white light, why is the sky blue?
That's a good question. Why is the sky blue?
Effects.
Okay, rainbow. Speaking of the rainbow, notice that the top is always going to be red, the bottom is going to be blue. Why? Furthermore, how does it form? What causes the rainbow? All right, so the white light going through a prism is going to break up into its color components. You got red on top, the blue at the bottom. Actually, it's red on top, the violet is at the bottom. So a couple of questions. What caused the light to break into its color components, break up into its color components? That's number one. Second question is, why is it that the color red is on top and the blue, the violet at the bottom? That's always the case. What caused that to happen? Stealth, making an airplane invisible to radar. How do we do that? There are a couple of ways of doing it, so we will discuss one of them. You got a meter stick, which is partially immersed in water. Notice that it looks bent. Why does the stick look bent? Okay, don't say it because it is, it's not. It's a straight stick, just put it into water like that, it's gonna look bent, so the question is why? And some of you guys will say, oh, because the light bends in water. So why does the stick look bent if that's the case? Diamonds. Diamonds are forever, right? Why do they sparkle? All right, so what's the sparkle and why do diamonds sparkle? Can you tell a fake diamond from a real one just by looking at it? We'll find out. All right, so we're going to be studying the electromagnetic wave spectrum, literally. So far, the only thing we've done is the electromagnetic waves in terms of we know something about the radio waves, and we talked about microwaves up to a certain point. All right, so, and then we discussed a little bit of heat. Study of heat is known as thermodynamics. We will actually go back and study this a little bit more formally before jumping into modern physics in order to make it interesting. Okay, guys, from now on, I'm going to start going easy on the math. Okay, so because the math is not that important at this from this point on, because we're going to dive into modern physics, the optics. I'll go easy on the math as well. I want you guys to kind of get the concept because now we're getting to the fun stuff, except the numbers won't make a lot of sense to you. All right, it's not like acceleration and force or whatnot. Just get the concept, and then I'm still going to give you some math problems because it's still 1/3 of your grade, but math portions of the test will be fairly straightforward from now on. All right, just find the formula, do the listing, and then just do the computation, and then do the interpretation. Yeah, but focus on the concepts. Okay, so the one thing that I want you to notice here is let's focus on the wavelengths. Okay, ignore the frequencies, let's focus on the wavelengths. I want you guys to do a comparison in terms of red versus blue, because I always look at the difference between red and blue. In reality, we should be looking at between red and violet. Okay, so I'll go with red and blue, and then when I say blue, I think violet is a better way of looking at it, but blue is as far as I'm going to go. All right, so which one is a larger wavelength? Is it red or is it blue? Okay, so 10⁻⁷, obviously this means it's microscopic, so which means that let's focus on the first two numbers. All right, so this is roughly about 8, this is roughly about 5. So the red has a much larger wavelength than blue does. That's the only thing I want you to remember. It's not important that you don't remember the numbers. Numbers aren't that important. It's the magnitude, the size of these numbers relative to each other is important. So red is a larger wavelength than blue. That's the only thing I want you to remember. To get the frequencies, focus on the wavelengths. All right, so something about light that we discussed. The light is being generated by electron undergoing a quantum jump inside atoms. All right, that's the way we usually talk about it. So the excited electrons, we say, generate light. Excited electron is an energized electron. That's what it means. How do you know that the electron is excited? Because it glows. Excited electrons generate light. Excited means energized electrons will generate light. So what they would be just jumping around inside the atoms. By that motion, every time they do a transition from a higher energy state to a lower energy state, every time there's a jump inward, the light is being generated. Electron becomes excited, becomes energized, jumps up, stays there for a fraction of a second. Upon jumping down, it's going to release that energy. So that energy gets released in the form of light. All right, just that's the only thing you need to remember until we get into modern physics. All right, so that's the modern physics explanation.
An oscillating electric charge creates waves.
Oscillating charge is the accelerating charge. Remember, speeding up, slowing down, changing direction, speeding up, slowing down, changing direction. All right, so the accelerating charges, the oscillating charges will generate electromagnetic waves
That propagate along the lines of force at the speed of light. These ripples are transverse waves in the electric field, propagating in wave fronts that become flatter and flatter farther from the source, coming more and more to resemble the plane parallel wave fronts that are called plane waves. As the wave fronts pass through each point in space, the electric field vector oscillates up and down, marking the passage of peaks and valleys of the propagating wave. Thus, an oscillating electric charge is indeed the source of outward spreading ripples in the electromagnetic field. It took James Clerk Maxwell's theory to explain the nature of light and to project the image of the electromagnetic spectrum as a whole.
Okay, so oscillating charge or the accelerating charge is what generates the electromagnetic waves, right? In this case, it's a pulsating sphere, so the oscillating charge inside the atom is the electron. All right, so electron is just oscillating, jumping inside the atom, so it generates the electromagnetic waves. If it's got the right frequency, it's going to be light. All right, so let's get back. So the electromagnetic waves are traveling in the opposite direction radially, in this direction. These are the wave fronts at the light speed. And if you draw lines perpendicular to these wave fronts, these are known as the light rays in essence. All right, so the distance between the wave fronts is known as the wavelength. All right, so you got these wave fronts, and you got the light rays, which are going to be perpendicular to the wave fronts. And that's what we will discuss. All right, so the incident ray, reflected ray. Incident ray is the incoming ray. So it's going to be incident to this reflective surface. It gets reflected. The angle of incidence is going to be measured with respect to the normal. All right, so it's going to be theta sub I is the angle of incidence. So this is the angle of reflection. If it's the law of reflection, according to which the angle of incidence is going to be the same as the angle of reflection. So the angle of incidence with respect to the normal is going to be the same as the angle of reflection. Incident ray, reflected ray, incident ray, reflected ray, incident ray, the reflected ray. Okay, something interesting about this. I don't know if you notice it. Notice that the intensity of the incoming ray is not the same as the intensity of the reflected ray. So which means that whatever the surface is ends up absorbing some of the intensity, some of the energy gets absorbed as well as the momentum. All right, so that's what we were talking about when we were dealing with the radiation pressure. Immediately you notice that this is a clearer line than this one is. Incident ray, the reflected ray. So once again, the intensity of the ray changes immediately. So which means that some of that radiation is absorbed by that surface. So the total intensity divided by the light speed is going to give you the radiation pressure acting on that surface. Anyway, so that's just an aside. So the angle of incidence is going to be the same as the angle of reflection. All right, so that's known as the law of reflection. You got the regular reflection. This is the mirror reflection. All right, so angle of incidence is the same as angle of reflection. And then you have irregular reflection, which is the sort of reflection that you get from surfaces which are not smooth. You see the surface, but you don't see your reflection. That's what it means. Regardless of what the regular or irregular reflection, the angle of incidence and the angle of reflection is always going to be equal to each other. Except the incoming ray, it's coming in this direction, it's going to get reflected in a different direction. So, which means that you're not going to be able to see the reflected image. Instead, you're going to see the object itself. That's what it is.
A century ago, Apollo astronauts set up reflectors on the moon. Today, they're targets for astronomers at the McDonnell Observatory, Texas. By bouncing laser beams off the reflectors, the speed at which the moon is receding can be measured to within a hair's breadth. The gap is widening by 1.5 inches a year. From this, over 4.5 billion years, the moon in our skies has shrunk to this.
Okay, so that little experiment
A century ago, Apollo
that they came up with using reflective mirrors, they're bouncing laser beams off the mirrors located on the moon, they notice that the moon is actually moving away from the Earth, roughly about an inch and a half per year, in essence. So the question becomes, wow.
They call it the black jet. The F-117 is the invisible man of the aviation world. The F-117 penetrated Iraqi air defenses undetected while making precision attacks.
As you see, the airplane is made almost entirely out of flat surfaces. Now, radar is an electromagnetic wave of energy. And when it hits a...
Okay, so the radar uses radio waves, right? Electromagnetic waves, just like light, angles will matter. All right, so you got the incident radiation and you got the reflected radiation. So if you angle it just right, the reflected radiation can get reflected in a different direction, so it doesn't go back to the radar
surface. It bounces off. When you hit the flat surface, it pretty much all bounces off in one direction.
While the F-117 is all angles, the B-2 stealth bomber is a smooth batwing, but both can slip through enemy air with relative impunity.
Stealth aircraft aren't really terribly fast or terribly maneuverable, but if they're invisible, it doesn't matter.
All right, so that's one way you can make things radar invisible. That's actually not correct. There's still going to be a radar cross section. All right, so instead of, if you're looking at a radar, it's not going to look like an airplane, but it's going to look like a big bird. So which means that you cannot be moving too fast. If you are moving way too fast, obviously it becomes fairly obvious that you're trying to penetrate their airspace, and you can't also go in a straight line. All right, so we've got a couple of problems. Number one, it's an airplane. It's not going to be able to fly like a bird. Also, these things will still go fairly fast. They're going to move much faster than the flock of birds. So which means that that radar cross section somehow has to be made of something that can absorb radar. Radar absorbing materials is something that they will get to use. So the question is, how does that work? So that's something that we will discuss later.
An even more important question.
All right, so we're dealing with reflection. So the question is, what causes reflection on the atomic scale? Obviously, you got the incident ray, hits the mirror surface, it gets reflected, and then you see a reflection, right? So what causes the reflection? What's happening between light and the atoms making up that structure?
Since everything ever seen is the result of light encountering matter, the question is, what is the nature of that encounter? And the answer is, since all matter is electrical in nature, it all comes down to light waves and electric charges. For example, when a light wave encounters an electric charge, the oscillating electric field makes the charge oscillate, which creates a new outgoing wave. Notice the shadow that forms behind the oscillating charge. A line of electric charges, they might be electrons bound to atoms in a crystal, can produce outgoing plane wavefronts in new directions. And if the charges are free to move easily, as are electrons inside a metal, the result can be to stop the wave from penetrating at all. Instead, the wave is completely reflected. This is mirror reflection, in which the angle of incidence is equal to the angle of reflection. That's true no matter from what direction the beam arrives. But reflection can also be described in a different way. Of all the possible paths from source to mirror to destination, the true path is the one that arrives in the shortest time.
All right, so the question is, what is reflection on the atomic scale? All right, so what's going on with the incoming electromagnetic wave and the atomic structure of the reflective surface?
Going plane wavefronts in new directions.
Okay, you kind of get the answer here, but let's come up with a better explanation, and then we'll finesse the explanation a little bit. All right, so this is chapter number 23 for you guys, the laws of geometric optics. Okay, so here's the incident ray. It's getting reflected. Incident ray, the reflective ray. Angle of incidence is going to be the same as the angle of reflection. This is your high school physics right there. All right, the stuff that we're going to be interested in, what goes on between the radiation and the atomic structure that causes reflection. Okay, so reflective surfaces, like the metal surfaces, will usually have free electrons, the conduction electrons. All right, so what do the conduction electrons usually do? Here's the incoming radiation. And then here's the electric field component of the incoming radiation. It's going up and down, so that's the electric field component. And you got the electron. What will the electron do? So when the radiation comes in and then interacts with the electron, it's going to jiggle the electron this way, right? So it's going to jiggle the electron. So the motion of the electron is going to create its own electromagnetic wave in essence. So now this starts to wiggle around and the accelerating charges generate electromagnetic waves. So the electromagnetic wave, all right, so the electromagnetic wave generated by the vibrating electron, the accelerating electron, is going to go in this direction. All right, so that's the short answer. Okay, so the question is, why is it that this electron, which is vibrating in this direction, is going to be vibrating in this direction, ends up creating an electromagnetic wave, which is being emitted only in this direction? And why is that the angle of the reflection generated by this electron matches the incident angle? All right, so that becomes the question. Okay, so all of a sudden, this simple explanation, it's got holes in it, in essence. All right, so incident radiation and reflected radiation, angle of incidence is going to be the same as the angle of reflection, right? So the angles are going to be the same. So that's your high school physics. So the explanation is you're going to end up getting a reflection only if the incoming radiation, it's got the electromagnetic field component. Charges will interact with the electric field component. The electric field hitting these negative charges will just oscillate these charges in this direction. Oscillating charges will create their own electromagnetic waves. So the electromagnetic waves generated by the oscillating charges somehow have exactly the same angle that matches the incident angle. Okay, so the question is why? So we'll check to see if we can even answer the question. So that's the reflection phenomenon. Refraction. It's the bending of light rays from a straight line and go from one medium to another, in essence. All right, so this could be glass, it could be water. This is air or vacuum. All right, so what's happening is the light enters into a medium which is denser than the incoming medium, or it's denser than the medium that the light is leaving behind. I don't like it. Okay, so light is going to bend towards the normal when it enters in a medium which is denser. When we say denser, we mean optically denser, in essence, whatever that means. It'll become clearer shortly. So every time the light changes medium, upon entering into an optically denser medium, it's going to bend towards the normal. So this phenomena is known as refraction. So the bending of light rays from a straight line is known as refraction. All right, so now let's reverse the process. If the light is coming from a denser medium into less dense medium, it's going to bend away from the normal. So it's going to get refracted away. If it's entering into a denser medium, it's going to bend towards the normal, so which means that it's going to get refracted towards the normal.
Here's a light trick that doesn't need mirrors. Put a penny in a pie pan. Now move back so you don't see the penny. Don't move, because I'm going to pour the water in. It's okay if you make a mess. Pretty cool, eh? See, light's always bouncing off the penny. But when you pour the water in, it makes the light bend. And the bending of the light makes the penny reappear. But the penny didn't move through all of this. But don't take my word for it. Try it.
Son, it's to learn.
See, light's always bouncing off the penny. But when you pour the water in, it makes the light bend. And the bending of the light makes the penny reappear. But the penny didn't move through all of this. But don't take my word for it. Try it.
Okay, so penny is here, but the penny is going to appear here, right? So the question is why? A lot of people say because of refraction. The answer to that question is no, it's not refraction, guys. Refraction is the light from the penny is going to get refracted into your eyeball. That's your refraction. My question is, why do you get to see the penny here? The actual location of the penny is here. Notice that the refracted image is not where the actual object is. So what's causing this phenomenon? Why is it that you end up seeing the image right here? Well, this is known as illusion. So refraction is what's happening. What's happening is the light is bending into your eyeball, which means that the light is coming from a denser medium to a less dense medium. So it gets refracted away from the normal. All right, and then the image is going to register on your brain, and then the brain interprets what it's looking at. Brain likes to see things in a straight line for whatever reason. So it reconstructs everything in a straight line. As a result, the image is going to appear here. So that's called illusion. So it's a reality that the brain itself makes up. By the time the world around us gets registered by the brain, optical nerves or whatever, everything is going to be upside down. So the brain turns things right side up, and then it provides a three-dimensional representation of the image that it's looking at, and it puts some colors in it. All right, so a lot of what we see is the interpretation of the brain regarding what reality is. All right, so that's going to become important when we start to get into modern physics somehow. All right, because things will get real weird pretty fast starting next week. All right, so refraction is what happens to the light from the penny into your eyeball. An illusion is the interpretation of the brain, and all of a sudden the refracted image is going to appear above the actual location of the penny. All right, so that's how refraction. Again, the stars that we're looking at are not quite where they are, right? We don't see the stars where, in terms of their actual locations, we see the stars appear at their apparent positions. That's what it means. Because of the fact that there's going to be optical aberrations, which means that the light is going to get refracted from these stars. And once again, we have a tendency to see things in a straight line. And all of a sudden, the actual position of the star and the star is going to appear at a different location, as far as we could tell. All right, so the next question is, what's causing refraction? Why is it that the light is bending in these optically denser media? The reason why the light is bending is because the light actually slows down in denser media. All right, so upon entering into glass, it's going to slow down. In water, it's going to slow down. And how much the light slows down is indicated by something called the index of refraction. All right, so the index of refraction for glass is 1.5, 1.5, almost 1.5, which means that in glass, the light moves 1.5 times smaller, give and take. Water is going to 1.33. So it's going to be moving about 1.33 times slower in water. Diamonds are forever. So notice that it's going to be moving about 2.5 times slower in diamond, 1.5 times slower in glass, 1.33 times slower in water. So the question is, how does the light slow down? That's the number one question. Number two, so it slows down. Why would the light bend? How do you explain that? So the refraction is the bending of light rays from a straight line. The light is going to bend every time it's changing medium. Every time the density of the medium changes, the light is going to bend. If it's coming from a less dense into a more dense medium, it's going to bend towards the normal, so that's your normal. If it's coming from a more dense medium into a less dense medium, it's going to bend away from the normal. So this is known as the angle of incidence. This is known as the angle of refraction. All right, so we got a bunch of observations. The first one, the light bends towards the normal, entering into a denser medium. It's going to bend away from the normal, entering into a less dense medium. The cause is because the light is going to slow down. Light slows down in an optically denser medium in general. So how much the light slows down? This is the speed of light in a vacuum, and this is the light speed in the optically denser medium. So how much the light slows down is known as the index of refraction and represents the index of refraction. All right, so V is the speed of light in an optically denser medium, and C is the light speed in a vacuum. All right, so N is going to signify how much the light is going to slow down in a denser medium. All right, so we got two different media, M1 and M2. N2 is going to have an index of refraction, which is going to be larger, so which means that this medium is denser than M1 in essence. All right, guys, bigger the index of refraction is, the denser the medium is. That's what it means in essence. All right, so incident ray, the reflected ray, refracted ray. All right, so the relationship between the index of refraction and the angle of incidence and angle of refraction is this. This is known as the Snell's law in essence. All right, so this is the Snell's law. Okay, so if you know the angle of incidence, you can figure out the angle of refraction, provided that you know the indices of refraction for these media that you got. All right, so what else do we have? All right, so the index of refraction, do I want to do a derivation for it? No, but I want to have a discussion. Okay, cool. So index of refraction represents how much the light is going to slow down relative to the speed of light in a vacuum. Okay, guys, here's the formula for the speed of a wave. In this case, this is the speed of an electromagnetic wave. So what's going to happen is, for a given frequency at the boundary, or just even if you don't understand, just go along with it. Eventually, magically, things will start to make sense. All right. So what's going to happen is, this is the light speed. You come in, and there's going to be a boundary between two different media. You come in from air, hit the water to air boundary. Imagine that the frequency at the boundary is going to be constant. So what's going to happen is the wavelength is going to change upon hitting this boundary. All right. So here's the speed of light in a vacuum, expressed in terms of its wavelength and frequency. And here's the speed of light in the denser, optically denser medium. All right, so this is the wavelength, which is going to be affected by the medium itself, the density of the medium itself. That's the reason why this is lambda sub n that we got. So if the frequencies are the same, if the frequency is constant at the boundary, so what that means is the wavelength is going to be affected by the index of refraction, which means that in an optically denser medium, the wavelength is going to get shorter by the index of refraction. All right, so what that means is the wavelength of the light is going to become shorter as the light is slowing down. So the wavelength is going to get shorter in an optically denser medium, which means that so wavelength is going to become shorter, whatever that means. That's
Right, in a different
sense.
way.
In a few minutes.
Of
Well, like the meaning of it is going to make sense.
all the possible paths from source to mirror to destination, the true path is the one that arrives in the shortest time. Because a metal surface with its mobile electric charges is just what it takes to bounce the light back. Mirrors are made of silver, which is plated onto the surface of glass. But if that's why mirrors work, why do lenses work? They work because when light travels through a transparent medium such as glass, the continual reconstruction of the light beam by each molecule of the material makes for slow going. In other words, the speed of light inside the glass is slower than it is out in the air. Arrived in a different way. Onto the arrives into the surface, travels through a light in glass. To destination. The path is the one that arrives in.
Yeah, your audio isn't working correctly.
All right, guys, give yourselves 5 points for that one.
The shortest time.
The video also seems to be partially blocked on my screen. It looks. Oh, nope, it's fine now.
Yeah, hold on. Okay, perfect.
Because a metal surface with its mobile electric charges is just what it takes to bounce the light back. Mirrors are made of silver. When light.
Okay, this thing is a minute long. It's almost like a textbook explanation of refraction, which is not an explanation at all. All right, so the question is, why does the light travel more slowly? A lot of textbooks usually come up with these equations like the Snell's law. And so you could do a bunch of computations. If you know the index of refraction for one medium, if you know the angle of incidence of refraction, you can figure out the index of refraction for the second medium, blah, blah, blah. Okay, I got that. But there's absolutely no explanation as to why the light slows down. So a lot of the textbooks put the emphasis on math. Physics goes unexplained. And we end up watching this video literally without learning much of anything. Right? A lot of the documentaries also lack a great deal of physics. All right, or they provide an explanation. You find these kind of explanations, the explanations started to appear more and more recently. And this is the most commonly seen explanation. Okay, we will build upon this explanation. So I'm just gonna go along with it. All right, so here's what's happening. Incoming light gets absorbed by the electrons of the atoms, making up the structures. Remember, the electrons can absorb light, energy in the form of light, and then they will become energized. They will jump up to the next energy level. They will stay there for a fraction of a second. And upon jumping down, they will release that energy, and then that energy is going to travel to the next atom. It's going to become absorbed by the electron or electrons. Electrons will just absorb the light. They will just jump up, and upon jumping down, they will release the light. Light is going to travel to the next one, and so forth. Okay, so notice that the absorption as well as the remission of light takes time. All right, that's the reason why the light gets delayed. According to your textbook explanations, that's a common explanation. All right, so what's missing in this explanation is, all right, so the light gets absorbed by electrons, and then they get reemitted, reabsorb, reemitted, reabsorb, reemitted. As a result, absorption and remission is going to take time. So as a result, it's like it's delayed in essence. All right, so while it's traveling from one atom to the next one, it's going to travel at the light speed. Absorption and remission delays it. Travels to the next one. Absorption and remission delays it. So the question is, why does the light keep traveling in the same direction after it gets absorbed and remitted? Because absorption and remission is also known as scattering, which means that after the light is absorbed and remitted, it gets remitted at a random direction. So all of a sudden you go, oh, that explanation didn't work out, but at least good try for the textbooks. Finally, they're moving in the same direction, in the right direction, I'm going to say, except that physics is lacking. Oh my God. I mean, physics get buried in this math. And then when you try to expose it, you see a lot of BS explanations as if these physicists don't really understand what it is that they're doing when you just take the physics out of the domain of mathematics. So all of a sudden the explanation is, it just doesn't make sense. If it's the absorption and remission of light, if that's the case, the light should be moving at random directions. The main light cannot be moving in the same direction. And furthermore, the next question is, why does the light bend just because it's slowing down? How do you explain the bending effect? All right, this guy is one of my favorites.
The internet is a
from Fermat.
very powerful tool, putting the knowledge of humanity at our
Absolutely provides the best explanation.
very fingertips. However, the internet is also a source of misinformation. You can hear all sorts of explanations, stated authoritatively and with good intentions, but also utterly and totally wrong. So in this video, I thought I'd address a common one and give a correct explanation for why light slows down in water. Actually, that's just a catchy title. I want to tell you why light slows down in any transparent medium, certainly water, but also glass, plastic, and even air. If you ever took a physics class, you learned about the index of refraction of a material. The index of refraction is just a fancy term for how much light slows down in that material. The index of refraction, always written as little n, is a number greater than 1, and the speed of light in a material is just the speed of light in a vacuum divided by the index of refraction. I put a table here to give you a sense of how much light can slow down in common materials.
This slowing down is the reason that objects look bent in surface water. It's because the path that the light follows bends when it enters or exits water. It's the reason that you can get pictures like this one here. And I should let you know that no physics teachers were harmed in shooting that photo. There's a ton of interesting phenomena I could show you that arises because of the index of refraction and the slowing of light, but I want to focus entirely on the slowing thing. So, to do that, let's look at this animation. So suppose you have a piece of glass with an index of refraction equal to 1.5. That means that light will travel at 2/3 the speed of light in the glass. If you shoot a laser at the glass, the light from the laser will travel at the speed of light until it hits the surface of the glass. When it hits the surface of the glass, the light will slow down to 2/3 its original speed, and it will change its direction. Once the light gets to the other side of the glass, it will emerge from the glass, change its direction, and move again at the speed of light. That's what happens. In addition, the light emerging from the glass will travel in exactly the same direction. Well, more precisely, in a path that is parallel to the direction of the incident light. The path is offset a smidge to the left, but the angles are the same. So that's what happens. It's been tested, and there's no debate on any of that. So now for the real question. Why does light slow down? And how can it speed up again when it leaves? There are two very common explanations that you find on the internet. Both of them are completely wrong. Let me tell you them first. The first one makes some kind of sense. It's wrong, remember, but it does make sense. It's the idea that light scatters off atoms as it passes through the glass. The light hits an atom and goes careening off at an angle, then hits another atom and careens off on a different angle. Light always travels at the speed of light between atoms. That process occurs again and again as the light passes through the glass, but let's focus on just these two scatters to see how the explanation goes. If we take away the atoms, we can see the important bits. There's the actual path traveled by the light in this scenario, which we can compare to the straight line path. If we straighten out the actual path, we see that it is longer than the straight line one. And if light travels at the speed of light in a vacuum between scatters, we see that it will take longer than it would if it went to straight line distance. Taking longer is another way of saying effectively going slower. And this is how some people explain the effective slower speed of light in glass. So how do we know it's wrong? Well, scattering isn't a precise process. Light can scatter in lots of directions. For instance, it could have scattered like we see here. This is a much more serious scatter with a much longer path, and consequently, light would effectively be much slower if this happened. Furthermore, there is no way to guarantee that the light would end up back traveling in the original direction. In fact, if light did what is being claimed, it wouldn't follow the path we observe. Instead, light would come out of glass with a range of velocities and a range of angles. This idea just doesn't work because it doesn't make correct predictions, so no good. The second wrong idea is that light is not scattered, but rather that it is absorbed and re-emitted by atoms. Between atoms, the light travels at the speed of light in a vacuum. The amount of time the atom takes to absorb and emit the light seems to slow the light down. You can see what I mean in this example here. The speed of the photons, while moving, is always the same, but the time taken during the absorption and emission makes the solid line take more time than the dashed one. This effectively makes light slower. Now, this idea, while sensible, is also wrong. Let's see why. The problem is that when an atom has been absorbed by a photon, it doesn't remember where the photon was coming from. And when it emits a photon, it can do in any direction. So what really would happen in the absorption and emission case is something more like this. The photon would be absorbed and re-emitted in a willy-nilly direction. In the end, the passage of light through the material would end up looking like this, which, well, isn't what we see. So if neither of these ideas work, what does? First, I should say that these two ideas kind of have buried deep at the bottom of them the idea that light is a particle. However, the reason that light slows down in material is better illustrated if one embraces the idea of it being a wave. There are many properties of a wave, and most importantly, the wavelength. The wave oscillates up and down with a separation between peaks and a time between oscillations. A second important property is what we call superposition, which is just a fancy way to say that you can add them. And adding them is easy. You just take the height of the two waves and add them together. If the two waves are lined up so the peaks are at the same place, the result is a single wave with a higher peak. If the wave is lined up so a peak corresponds to a trough, then the two waves cancel. And if one wave has a different wavelength than the other, you end up with a funny looking shape. That's just how it works. It gets more interesting when one wave is moving at a different speed than the other one. The result is a different wave, but one that has a different speed than either of the two. That's super important, so let's just take a careful look at it. If we add the two top waves, which have different speeds, the bottom wave also moves, but slower. So let's get back to light moving through glass or water. Remember that light is a wave of electric fields. It oscillates with a characteristic wavelength and frequency. That wavelength depends on the color of light, with blue light being about 400 nanometers and red light being about 700. Numbers don't matter as much as that you remember that light is changing electric fields. Now, of course, glass is made of atoms, which are surrounded by electrons. Electrons have an electrical charge, and that charge feels a force from the oscillating field of light. Because it feels a force, the electrons move. But moving electric charges also set up their own oscillating electric field. Said simply, the oscillating electric field of light makes electrons move, which makes a second oscillating electric field. And if you have two oscillating electric fields, that's two oscillating waves, and you can add them together just like we saw before. The net effect is that the two waves combine and make a single wave of oscillating electric fields. And that is the wave that moves through matter. And this is important, it moves at a slower speed than light does in a vacuum. This also explains something that many people were confused by. Most people were willing to accept that passing through glass would slow down light, but they were very puzzled about light speeding up when it left the glass. That seemed like it created energy, and well, that didn't make any sense. But now I hope it does. Before light hits the glass, it travels at the speed of light in the vacuum. When it passes through the glass, the light causes the electrons to move and generate a second wave that adds to the light. Light still moves at the speed of light in the vacuum, but the wave from the electrons move at a different speed, and the combined wave moves slower than light would if the atoms weren't there. Then, when light leaves the glass, there are no atoms around to make electric fields to add the light, and then light speeds along at the preferred vacuum speed. So that's it. Light effectively travels slower through material because when it is in material, it generates a second wave that combines with the light, and the combined new wave moves slower than the familiar speed of light. Ta-da! All right, so tell everyone, this is something for which you often hear wrong.
So resultant electromagnetic wave, combination of the original electromagnetic wave of the light and the electromagnetic wave generated by the vibrating electrons, end up moving slower within the material itself. All right, so that's the reason why we say the light slows down.
Explanations on the internet.
So the next question is, why does the light change direction? Why does it bend?
Now you know, and that means you're eligible for membership in the Physics Cool Kids Club.
So why does the light bend inside an optically denser medium? Okay, guys, these are your test questions. So I'm talking about the conceptual portions of the test, so I just focus on that one. Okay, so a couple of things that, okay, let me just go over the blah blah first. A couple of things. All right, so the book explanation first. All right, so incoming light hitting an optically denser medium. So what's happening is the wavefront, the distance between the wavefronts will be the wavelength. And then the light is going to slow down. So the wavefront is going to hit the medium. As soon as it hits the medium, it's going to slow down. The next one is going to slow down. The next one is going to slow down. And as a result, what happens, the distance between the wavefronts is going to get shorter. What that means, the wavelength is going to get shorter. All right, so I had given you some kind of mathematical derivation for it. But mathematical derivations are usually not the best way to understand this stuff. This stuff is kind of visual. All right, so upon change of medium, the light is going to slow down for the reasons that he explained, Lincoln explained. So the next question is, notice that the wavelength is going to get shorter. The frequency is going to remain constant. The wavelength is going to get shorter. And then the light changes direction. So the question is, why does the light change direction? Why does the light bend upon entering into a denser medium? The best analogy, this is not even an explanation, this is an analogy that I see time and time again. I don't want to say the best one. The most common seen analogy in these physics books is this one. For whatever the reason, I'm always referring to Survey. All right, so here's a barrel rolling on concrete, and then it's going to hit grass. Right, so here's the leading edge. It's going to catch grass, and it's going to slow down. So when the leading edge slows down, what happens? The entire barrel is just going to change direction. It's going to twist in this direction. All right, so the same thing is going to happen to the light rays or wavefronts that you're looking at. All right, so now that's the explanation that you end up seeing. But the reality of it is, if you're dealing with a barrel, the surface of the barrel, the atoms are rigidly attached to each other. So you're dealing with a rigid surface. So if you slow down this end, obviously this end is speeding up, the entire structure is going to turn. If you're dealing with the wavefronts, these things are not rigidly attached to each other. All right, so I can see that this end's slowing down, but that doesn't explain why the entire structure just ends up bending towards the normal. So which means that we have to come up with a better explanation. So this explanation alone just doesn't make a lot of sense. So why does the light bend? So this is the last one that we will do for today.
I've made a lot of videos, but a recent one somehow engaged many viewers. This video was about why light slows down when it enters water, glass, or any transparent medium. For some reason, this video took off, and the comments were very interesting, covering the entire gamut of claiming that the video was insightful to claiming that it was utter rubbish. But one particular question appeared over and over again, and that comment was, but why does light bend when it goes from air to glass? And it's true that I didn't answer that question because, well, it wasn't what the video was about. But a lot of people ask, so in this video, I thought I'd tell you why. Now, as it happens, there are lots of wrong explanations out there, lots. So the first thing I'm going to do is tell you the wrong ones and why they're wrong. Don't be surprised if I debunk one you learned. So let's start with what we see when a beam of light hits glass. Light traveling through air will change its direction when it hits the surface. The amount that its direction will change depends on the angle at which it hits the surface. Change the incident angle, and the transmitted angle will change correspondingly. Those angles are related through a physics formula called Snell's law, named after Dutch astronomer Willibord Snellius, who lived in the 1600s. I have his formula written over here. If you'd like to learn how to use the formula, there are many online tutorials, but I'm not going to cover that here because I want to get into the question of what is the physical process that causes the path of light to change as it enters the glass. So let's get into it. There are three commonly suggested explanations that are wrong, or at least incomplete. They are Fermat's principle, the analogy of soldiers marching, and Huygens principle. Fermat's principle says that light will travel from one point to the other, taking the minimum amount of time. It's often explained in terms of a lifeguard and a drowning swimmer. In order to maximize the chances that the swimmer will be saved, the lifeguard needs to get to them as soon as possible. So what path does the lifeguard take? He could run directly to the water and start swimming. This means he would swim a long distance, but because he can run so much faster than he can swim, that would be a bad choice. So you'd think that he might just run over to the point where the swimming portion is shortest, but that turns out not to be the shortest time either. Then there's the straight line path. And because the shortest distance between 2 points is a straight line, you might think that this is the fastest path. But because swimming is slower, it still isn't the shortest time. It turns out that the shortest total time, that is to say, when you add both running and swimming time, is exactly what you get from Snell's law for light. You run a little longer than you would for the straightest path, but that means that you swim a little less and the total time is shortest. And that's exactly what light does. It follows the path of shortest time. But while that's true, it doesn't explain anything. It just says what it does, not why it does it. So that's not an explanation, and we need to come up with a proper reason. Let's look at the second option on the list. A very common explanation used to teach why light bends involves soldiers marching over firm ground, but then who encounter mud, although not all soldiers hit mud at the same time. The idea is simple. The first soldier who encounters the mud cannot move as quickly as the rest of the soldiers, so he slows down. Each soldier hits the mud in turn, resulting in a direction change. Eventually, the lines of soldiers are moving in a different direction at a different speed. This is how it's often taught. The problem is that this doesn't work. In fact, the soldiers will slow down, but their direction doesn't change. They will continue to walk in the same direction, but with marching lines that are slanted compared to how they started. This explanation gets the angle of the lines of soldiers right, but not the direction of travel. In fact, the only way that this explanation can be right is if the lines of soldiers are rigid. Then, the first soldier hitting the mud puts a torque on the entire line, and that would work. The problem is that this torque means that the soldiers on the top of the screen move faster, which is to say that if they were light, this part of the beam of light would have to move faster than light. So this explanation doesn't work either. Okay, so far we have a non-explanation and a wrong explanation. What about Huygens principle? Huygens principle, named after Dutch physicist Christian Huygens, depends crucially on the wave nature of light. We know that when a wave encounters a small gap, the wave passes through the gap and spreads out. This principle is called diffraction, and it's universal to all waves. If waves hit more than one gap, each gap will allow waves to pass through and make ringlets. The waves from each gap can interfere with one another, with the waves either adding to or subtracting from one another. In this animation, the lines show the position of the peak of the waves. Showing how the waves add together is perhaps easier looking at them from the side. When the peak of two waves encounter one another, the result is a single and bigger wave. And when a peak of one wave hits the trough of another wave, they can cancel each other out entirely. What Huygens claimed is that there is no need for gaps. Each and every spot on a wave was acting like it went through a gap and was spreading out. Now we can take that idea and have waves moving in one medium transition to another medium where the speed is different. So we can take light traveling through air and shoot it through glass. And because we're interested in explaining the bending behavior, we'll have light hit it at an angle. Here's how the Huygens explanation goes. What happens is that the wave peaks hit the glass at different times. The waves then spread out and begin to interfere with one another. Notice that the wavelength is shorter in glass. That's because the wave is moving more slowly. Where the lines accumulate, that's where the waves add to one another. And they don't just line up in one spot. They line up again and again. Remember that the lines denote the top of the peaks of the waves. We can see that there are many places where the peaks line up. We can overlay a couple of lines that show the direction that the wave is traveling and then remove the circular waves, and we see that this explanation seems to be doing a good job of predicting what happens when light goes from air to glass. Looks good, right? But not so fast. What happens when we look at all of the waves coming through the glass? Things get a lot more complicated. We do see that the waves add together to predict the direction that light moves in glass. On the other hand, that's not the only alignment. For instance, we see other geometries where the waves line up. there are the wave fronts that are going this way, and then there are the wave fronts going this way. So that's a problem. It seems that this approach doesn't give a unique prediction. Okay, we've ruled out Fermat's principle, the solder analogy, and Huygens principle. These are all often seen as explanations of the cause of refraction given by people who really do know some physics. So what's the real answer? It turns out that the only way to really answer the question of why light bends when it goes from air to glass is to get serious about the nature of light and to embrace the fact that it is made of oscillating electromagnetic fields, and that means you need Maxwell's equations. Because this isn't a full-blown physics class, I'm going to focus only on the electric fields, and I'm not going to do the derivation because that's the fun part. I'll leave that to you. But the big ideas are actually pretty straightforward. You start with Maxwell's equations, which are always beautiful to see. They're a little scary looking, but the question we're trying to answer is an easy one, which makes the whole thing a lot simpler than you'd imagine. In fact, we're going to need only the bottom two equations. So let's see what's going on. We start with light going from air to glass, hitting the surface at an angle. In our figure, we can replace the waves with the direction of motion. Now, it turns out that the electric field of light is perpendicular to the direction that light is traveling, and we can add that field direction to the diagram. And it's very important to remember that this field has a component both parallel to the surface of the glass and one that is perpendicular to the glass. And here is where Maxwell's equations come into play. Two copies of the equations are written here, one that covers when light is traveling in air and one where it is traveling in glass. So here's the key point. The surface belongs to both the air region and the glass region. This means that at the surface, the equations on the top and the equations on the bottom have to apply. And with that little bit of calculus, you can find two important restrictions. The first is that the electric field parallel to the surface of the glass has to be the same in the air and the glass. And similarly, perpendicular to the surface, what has to be the same is the electric field times this epsilon, which is different for each material and depends on its molecular makeup. We can then manipulate these equations to see what the electric field in glass should look like. Because epsilon is bigger in glass than in air, that means that the perpendicular electric field in glass has to be smaller than it is in air. Now we remember that the direction the light travels is perpendicular to the electric field, so we can put in an arrow to show the direction light must travel in the glass. And finally, we can see what light does when it enters glass or water or any transparent medium. It bends. And the reason that it bends is because the epsilon in glass is bigger than in air. Okay, what I just showed you is an equation thing. You're probably asking yourself what that epsilon actually physically means. It's there because of how the electric fields from the light interacts with the matter in the glass. You start out with glass with no electric field in it. The glass has charges in it, but they're arranged in a random way. But when you send light in, you impose an electric field on it. That field makes the charges move around, which sets up a counterbalancing electric field from the charges. The result is that the electric field in the glass is lower than it is in air because of how the electric field from the glass is in the opposite direction. And this is the reason that the perpendicular electric field is lower in glass. And that, my friends, is why light bends when it goes from air to glass. It's not because of many of the ordinary explanations. It's because of how light interacts with glass and changes the glass's properties. And it's because the electric field inside the glass is affected by the arrangements of atoms and molecules in the glass when light hits it. It's the same reason why light slows down in matter. Inside matter, the electric field due to the light and the electric field due to the matter both have to be taken into account. Outside, they go. And now, you know some serious physics. Light hits the glass, it travels at the speed of light in a vacuum.
So here's the incoming light.
When it passes
And that's going to hit glass. So index of refraction is going to 1.5. So the light is going to slow down. So
through the glass, the light causes the electrons to move and generate a second wave that adds to the light. Light still moves at the speed of light in a vacuum, but the wave from the electrons move at a...
All right, so what's happening is the light starts to go through the material. It's going to jiggle the electrons within the material. So what happens when you accelerate these charges? They generate their own electromagnetic waves. So there's going to be a wave interaction between the incoming wave and the waves generated by the electrons. All right, and then when they combine the speeds of these two waves, they're going to add up. The resultant wave is going to be moving 1.5 times slower.
Different speed, and the combined wave moves slower than light would if the atoms weren't there.
All right, so there's going to be a combined wave. You got the incoming wave, and on top of that, the wave generated by the electron.
Then, when light leaves the glass, there are no atoms around to make electric fields to add the light, and then light speeds along at the preferred vacuum speed. So that's it.
All right, so that's the best explanation I've heard so far. All right, so Don Lincoln's explanation is the one that I'm going to go with. I'm kind of partial because the guy is really good at what he does. He's at Fermat. Also has quite a few books that he published. So he's an amazing scientist. Also, he's one of the best explainers of physics. And then next question is, the bending of light rays, what's causing them to bend? All right, this one is a little bit tricky. It's also related to something that we discussed before. I'm not sure how well you will get it, but I'll try.
Switch or surround,
okay.
And it passes.
He tries to come up with mathematical explanation, which is fine. I get it. Okay, it doesn't need to be explained.
Through the glass, the light causes the electrons to move and generate a second wave that adds to the light. Light still moves at the speed of light in a vacuum. Well, everyone, this is something for which
Okay, obviously we got stuck on them. So why does the light bend?
the electric field parallels, because that's the fun. That little because of how the electric field, which sets up a count and depends on its molecular.
Okay, so let's check to see if we can come up with a better explanation for this one. All right. All right, so here's the incoming light. This is the electric field of the incoming light. Notice that the electric field is pointing in this direction. All right, so you can break the electric field into two components. Okay, so you can make a small triangle at this point. All right, so this is the perpendicular component, it's perpendicular to the surface, and this is a parallel component, the same parallel to the surface. Okay, so that's the explanation that he goes with. All right, the parallel component on this side of the boundary and at this side of the boundary is not going to change, because it doesn't matter that it's in this direction and that direction, it's not going to change. The perpendicular component, when it enters into glass, the glass is an insulator, it's a dielectric, guys. It's a dielectric. So what happens to glass? It becomes polarized. All right, so what's going to happen is if the electric field is pointing in this direction, all right, so it's gonna end up polarizing glass. Okay, let's
You
check.
can then manipulate these equations to see what the electric
Ignore the
is
equation.
there. That means that the perpendicular electric field.
All right, so the electric field comes in, and then it's gonna, what it's gonna do is, I can talk about it, but you're not talking about it does not do justice. All right, so what's gonna happen within the structure? Because as soon as the light enters into the glass is gonna become polarized. So here's the original electric field. So what it does, it's gonna push the positive charges in the opposite direction, and the negative charges will move in the opposite direction, right, inside glass. So it becomes polarized. And then, which means that there's going to be an induced electric field pointing in the opposite direction. So this is the induced electric field. All right, so here's the induced electric field. I'm going to put I. And this one is the original electric field. So the original electric field is pointing in the opposite direction. The induced electric field is going to point in the downward direction. So the induced electric field is going to be, it's not going to be as strong as the original one. So what happens, the total electric field means cumulative, which means that you have to add this to that. So there's going to be a vectorization, just like dielectric materials inside capacitors. What's going to happen is the strength of the electric field within the material itself is going to diminish. So what that means is instead of this being this long, it's going to become shorter. All right, so this is the new electric field. This was the original electric field. Remember, this minus this is going to give you this. The parallel component is still the same. It's going to be exactly the same length. So I'm just going to make this the parallel component. And then now this becomes the hypotenuse. All right, notice that the hypotenuse now no longer is pointing in the same direction. The hypotenuse right now is much flatter. All right, so this angle that you're looking at, I'm going to call this the new angle. All right, so here's the angle of incidence in this case. And this becomes the angle of refraction. I think that kind of makes sense under the circumstances. So which means that the entire wave ends up changing directions. So this is good enough. This is the explanation that he's going after. Once again, I like his explanation the best. But the question is, how well
glass.
The question is, how well do you grasp the concept?
It has to be smaller than it is in air.
So that's what he's saying. All right, so which means that the resultant electric field is going to be smaller after the polarization within glass because it's a dielectric material. As a result, what happens to the hypotenuse that you're looking at? This is the electric field. It's no longer pointing in the same direction. Notice that it just got tilted. All right, and this is the direction now the ray is moving in this direction. So that component that you're looking at, let's just draw this out one more time. Okay, so I'm just gonna connect the dots. This is almost like grammar school at this point, almost a straight line. All right, so this is the direction the wave is moving. Now it's moving at the speed. It was moving at the light speed before. All right, notice that the wave changed direction at that point. So that's the explanation. That's the reason why the wave changed.
Now we remember that the direction.
All right, so a couple of things.
When a light beam, incident at an angle, first encounters a piece of glass, one side is slowed down before the other, forcing the wavefront to change direction. This bending of light, whether in glass, water, or any other transparent material, is called refraction. Light is refracted closer to the direction perpendicular to the interface, whenever it enters a medium that slows it down. This occurs no matter what the direction of incidence. And as in the case of reflection, of all the paths that light could follow from source to destination, the one that arrives in the shortest time is the true path.
All right, so a couple of questions. All right, so what happens to the wavelength? All right, these are known as wavefronts. All right, so the darker lines are known as the wavefronts. The distance between the wavefronts known as the wavelength. Notice that the wavelength gets shorter. All right, so upon entering into a denser medium, wavelength is going to get shorter, and the light is going to slow down. And this happens provided that the frequency at the boundary is constant. So let me say it again. Wavelength is going to get shorter. If the frequency is constant at the boundary, wave is going to slow down. Let me say it differently. Because the wavelength gets shorter, and because the frequency at the boundary is constant, wave is going to be moving slower in a denser medium. All right, so normally, typically, the professors would say, because the frequency at the boundary is constant, because the wave is moving slower, the wavelength is going to become shorter. All right, so there are many ways of saying it. It doesn't matter. Everything that I said is knowledge. Or I can degrade it. I can say information. All right, so I'm just giving you the information, the knowledge. So what's happening is at the boundary, the frequency is constant. And because the frequency is constant, because it's moving slower, the wavelength is going to get shorter. You could do it mathematically, or you could just talk about it just like that, as if it's poetry. And now what do you have on the test? Of course, I'm not going to ask you that because it's not. I wouldn't ask you anything that you can Google. Yes, hopefully you guys are noticing it. All right, you cannot Google understanding as it so happens. It's not going to happen. All right, so welcome to college. What I'm going to ask you is, why is the frequency constant at the boundary? All right, so what makes the magic happen? So it slows down because it's obviously a denser medium. We came up with an explanation as to why it slows down. And we came up with an explanation as to why it changes direction. And we made the assumption that the frequency at the boundary is constant. As a result, the wavelength is going to become shorter. All right, the wavelength became shorter because of the assumption that the frequency at the boundary was constant. So why is it that the frequency across the boundary does not change? And you know, this is a test question. I'm sure you're thinking about it. Again, use for you. This is something that I asked when I was a graduate student, because we had a new guy from Harvard. It was fresh out of graduate school when I was in graduate school, and he was really, really unbelievably cocky. And he was looking down on us. It was the first lecture or whatever, and he was also my research advisor. For whatever the reason, it's decided to just tease him a little bit. And so this was the lecture. He's just giving this lecture. This is like 800 level course. It's the last theoretical physics course, or the most difficult one that we had to take. And so there are 2 hours of derivations, nothing but derivations. You have blackboards on every single wall. Everything was filled up. So eventually, he was doing the derivation. He just said, well, you know, because the frequency is constant at the boundary, you know, the wavelength is going to be shorter, obviously, right? But he said it in such a way that all of a sudden I got, oh, I got the sense that he didn't know why. Something was lacking, a bit of confidence, which was lacking. Because when you start teaching initially, there are ways you can compensate for what you don't know, right? Especially when you're a graduate student. A lot that you don't know, that you have to teach. And then that's when instructors usually focus on the knowledge stuff. And over time, when you become really seasoned, you go, oh, so that's information, let's focus on real physics. And that's what we're focusing on right now, obviously. All of a sudden, because what makes the magic happen, the reason why all of a sudden we go, oh, the wavelength gets shorter because of the assumption that the frequency at the boundary is constant. So I had the sense that he probably didn't know. And so at the same time, I'm a little bit hesitant because I'm not sure if I should embarrass him. The reason is because the guy's my research advisor at the same time. So I didn't want to really piss him off. So my best friend, Tom, my office mate, was sitting next to me. I said, oh, I bet the instructor doesn't know why the frequency at the boundary is constant. Should I ask him? He goes, yeah. He didn't even think twice. He said, oh, yeah, ask him. I said, what if he doesn't know? Oh, it's not a big deal. We'll laugh at him. Thinking that's not the best way to go. He said, he'll take it. He's from Harvard. He's probably has an explanation. I'm hoping to think that he doesn't know. And sure enough, I was right. He got stuck. That question really stumped him. Big time. All right. He could not explain it. The only explanation that he came up with was, well, we know that the light slows down, all right, in an optically denser medium. And we know that the wavelength is shorter, so which means that the frequency at the boundary must be constant. And that took him like 5 minutes to figure that out. without Googling anything, because you couldn't Google anything. Google didn't exist 20, 25 years ago. And he was supposed to know that stuff. The reason why he couldn't figure it out is because this is visual, not mathematical. These guys are theoretical physicists. You got experimentalists and you got theoreticians, and the way experimentalists and theoreticians think are completely different. This guy was not able to think outside of math. He was looking for what was constant at the boundary. His explanation was, it slows down, we know the wavelength is smaller, all right? So the frequency must be constant. It's very empirical. The reality of it is, you have to get back to the definition of frequency. And this thing is visual, it's beautiful. All right? My approach to physics is very conceptual, usually. I want to be able to visualize it. That's the reason why I tend to have a better grasp of what's going on sometimes, not all the time. All right, so this is one of those instances. All right, guys, frequency is the number of cycles per second, number of wavelengths per second, number of wavefronts per second. Okay, here's one wavefront, here's the second one, here's the third one, here's one wavelength, second one, the third one. So it's number of wavefronts approaching 1 second to the boundary, and the number of wavefronts crossing the boundary per second, they are the same. Notice that 1, 2, 3 are approaching, and 3 of them crossing within the same time period. That's the reason why the frequencies on both sides will be the same. All right, so the frequency at the boundary will remain the same. And notice that this wavefront is moving slower than that. As a result, the wavefronts start to bunch up together. All right, so what happens, the wavelength is gonna get shorter. I didn't have to do any math. Okay, you can visualize this. This is beautiful. When you do the math, obviously, when the frequency is constant, the only reason why the wave is gonna move slower if the wavelength is shorter. All right, that's how the math works out. But the conceptual understanding, being able to visualize this stuff is much better than being able to do it mathematically, because this is, you're really capturing the reality at its most fundamental level. Frequency is constant, this slows down as a result, the wavefronts bunch up together, which means that they slow down, the wavelength gets shorter as a result. All right, not too often in modern physics, you can come up with something that's visual or visually elegant. So modern physics is done in the complexity of abstract math usually. Even that you can visualize up to a certain point. All right, so wavelength gets shorter, guys. I talked about it for 20 minutes, hopefully you will remember. All right, so in an optically denser medium, wavelength is gonna get smaller because wave is moving much more slowly. And the frequency remains constant because the frequency represents the number of wavefronts approaching and crossing. They will be the same. All right, so we talked about it. So hopefully you caught it. Like, index of refraction increases. What that means is the light slows down. All right, the more the light slows down, the closer the wavefronts will be to each other. So which means that the smaller the wavelength is going to become. Is the best answer. All right, what do I want to do with this one? All right, let's use the Snell's law. I think we should do a few problems, at least one. All right, incident rate, angle of incidence. Here's the refractive rate. In this case, the light source is in the in air. In the second case, the light source is going to be in water, so it gets refracted away. Snell's law. Okay, I'm not sure if I want to do a derivation for this one. Let me check to see. Yeah, I'm not interested in. I don't care about the derivation for you guys. All right, so you guys are college students. Let's focus on the application of it. So what do we have? We get a light ray coming at 40-60 angle with respect to normal. So that's the angle of incidence that we got. So this is that angle. So it says find the angle of refraction relative to the normal. That's what we're looking at. From air to water. So N1 is going to be air. N2 is going to be water. So it's going to be what is 1.33. Okay, so that's water. And then this time we're going to change the scenario. This time, in part B, the light is going to be coming out of water into air. So that's what it is. All right, so Snell's law, angle of incidence, angle of refraction. Solve for the angle of refraction. Get rid of N2. And then isolate the angle of refraction, or theta 2. So by taking the reciprocal or inverse sign on both sides. That's it. That's as far as it goes. I'm not sure if I did the numbers for this one. Yeah, okay. And then you do the same by reversing it. All right, so I didn't put the numbers in, but that's how it is done. That's gonna go. Okay, let's do this, and then I'm going to put you guys into groups for a quick review. All right, refraction. Total internal reflection is what I'm interested in. Okay, so let's time the light sources in water. All right, so here's the angle of incidence. This is the angle of refraction. All right, so more dense into less than medium, it gets refracted away from the normal. And at this angle, notice that the refracted ray is going to be parallel to the boundary. And when the angle of incidence is like that, refracted ray is going to get, there's no refraction. So angle of incidence is the same as angle of reflection. All right, so this is known as total internal reflection. Let's focus on this angle, theta sub c. Okay, when the angle of incidence is smaller than theta sub c, light is going to escape from the material. When the angle of incidence is larger than theta sub c, you end up getting an internal reflection. All right, so what does theta sub c represent? All right, guys, this is known as the critical angle. It's called the critical angle. All right, so critical angle, why do we call it the critical angle? We call it the critical angle is because it is critical to figuring out whether the light escapes from the material or captured by the material. All right, so if the angle of incidence is smaller than the critical angle, light is going to escape. If the angle of incidence is larger than the critical angle, light is going to be captured. All right, so angle of incidence is larger than if the angle of incidence is smaller than critical angle, it's going to get refracted out. If the angle of incidence is larger, the light is going to be internally reflected. That's what it means. Critical angle is here. Angle of incidence is smaller than critical angle. Light escapes from the material. Angle of incidence is larger than the critical angle. It's totally internally reflected. Okay, so what happens at the critical angle? How do we know what the critical angle is? Well, you know what the critical angle is because at the critical angle, refracted ray is going to move parallel to the boundary. That's how you know. At the critical angle, so when the angle of incidence is the same as the critical angle, refracted ray is going to parallel to the boundary. So it moves parallel to the air-water boundary. Angle is larger than the critical angle, internal reflection. Angle is smaller than the critical angle, light escapes. That's it. All right, so let's capture that. Okay, this is, all right, this is going to be an easy derivation, so this is fine. All right, so here's the normal. All right, here's the incident ray. Here's the refracted ray. Notice that the refracted ray is moving parallel to the boundary, which means that this angle is the critical angle. So the angle of incidence becomes the critical angle. So in the angle, so the angle of refraction is going to be 90 degrees to the normal. So we'll get to use the Snell's law for that. All right, so let's make a decision. All right, so angle of incidence is the first one. So this is the angle of incidence. N1 is going to be this medium, N2 is going to be the other medium. Here's the angle of refraction. This is going to be 90 degrees. This is the second one. All right, so here's the angle of incidence. This is the angle of refraction. Sine of theta, 90 degrees. When theta is 90 degrees, it's going to be 1. So N1 is optically denser medium. N2 is less dense medium. So N1 is going to be bigger than N2. All right, so at this point, okay, because the angle of refraction is 90 degrees, this will give us the critical angle. That's the reason why I changed that to I became C. All right, so solve for the critical angle. When you solve for the critical angle, this is what you come up with. N2 roughly about 1. All right, so this becomes the critical angle formula. So now you can figure out the critical angle of just about anything. If it's glass, N1 is going to be 1.5. If it's diamond, it's going to be 2.5. If it's water, it's going to be 1.33. So the critical angle is going to depend on the medium. So higher the index of refraction is, the smaller the critical angle is going to become. All right, so higher the index of refraction, the smaller the critical angle. So bigger the index of refraction is, smaller the critical angle. All right, so the diamond is going to be much larger than air, so which means the diamond's critical angle is going to be the smallest. All right, so the diamond's critical angle is going to be the smallest. All right, so if the angle of incidence is larger than the critical angle, you end up getting an internal reflection. So the angle of incidence is larger than the critical angle, internal reflection. If the angle of incidence is smaller than the critical angle, all right, so the angle is larger than the critical angle, light gets internal reflected, so which means that light is going to be captured. At angle smaller than the critical angle, the light is going to escape from the material itself. Cool. I needed the number for that one. It's going to be less than 45 degrees. All right, I needed to see the number. All right. All right, so the technology is being used. Obviously, if you have prisms, or that physics is being used in the binoculars that we're looking at. All right, notice that you can keep changing the direction of light in essence, and then.
Which one of these do you think will excite you?
I really like that one.
Okay. This is the 3-carat round classic mounting set in platinum.
It's really pretty.
I hereby pronounce you engaged.
This is it. This is the one. Looking at rings has been great today.
Which one?
All right, so 2 questions. Number 1, why do diamonds sparkle? And number 2, what's the sparkle? All right, let's see the sparkle first. Okay, I'm gonna see a sparkle. All right, believe it or not, this thing, you're looking at it exactly at the right angle. And if you keep looking at it at this angle, notice that the diamond looks lit in essence, okay? If you move the diamond back and forth, this is something that you would experience as a sparkle. Sparkle is what you experience when the light escapes from diamond. All right, the light is gonna escape from diamond. Light is gonna escape from diamond at only certain angles. So which means that you get the impression of a sparkle when you're moving it back and forth or side to side in essence. And if you keep looking at exactly at that angle, it's gonna look like the diamond is lit. It almost looks like it looks like the source of light. Okay, right there. If you keep looking at it from this angle, it's gonna be shining. It looks shiny in essence. But if you keep moving it slightly side to side, just like that, it's gonna look like a sparkle. All right, so if you keep looking at a given angle without moving it, it's gonna look shiny, it's gonna look lit. All right, so why do they look sparkly? Why do they sparkle? Or why do they look sparkly? All right, so the sparkle is what you experience if you're looking at escaping light from diamond, in essence. If you keep looking at it at the same angle without moving the diamond back and forth, it's only gonna look shiny. All right. The reason why the diamonds sparkle, or they will look shiny, depending upon how you're looking at it, is because they're really, really good at capturing light. The reason why they're good at capturing light is because they have very small critical angles. Their critical angles are extremely small. All right, and then obviously the way they're cut matters. Right? They're cut in such a way that most of the light, upon entering into diamond, whenever they hit the boundaries, they're going to end up hitting the boundary at an angle larger than the critical angle. So what happens? They are just going to get bounced around. So the light is going to keep bouncing around until it finds a surface, and it's going to be able to hit that surface at an angle smaller than the critical angle. So which means that the light is only going to escape from certain angles. If you're looking at it from that angle, it's going to look shiny. If you keep moving the diamond back and forth, and then it's going to look sparkly. That's what it means. All right, so what is it that I'm interested in this case? So here's diamond, the index of refraction of diamond. So which means that the light is already inside diamond. All right, so the question is, I don't know. All right, so let's figure out, okay, so incident angle is going to be 28 degrees. So the question is, will it become captured by diamond, or is it going to escape? So will it get internally reflected, or will it get refracted? All right, so which means that we have to look at the critical angle. If this angle is larger than the critical angle, then obviously it's going to be captured by the material. So there's going to be an internal reflection. If this angle is larger than smaller than the critical angle, the light is going to escape. All right, so let's figure out the critical angle. So hopefully I come up with a number this time. All right, this is going to be 24 degrees. This is 28 degrees. So which means that it's hitting the boundary at an angle larger than the critical angle, which means that this light is going to be internally reflected. So it's going to remain inside the material. So critical angle is smaller than this angle, so therefore the light is internally reflected. So it's going to get captured by the material. All right, so next question is, what would happen? Hopefully, let me check to see if I've done it. Okay, it's long enough. All right, so this time, what would happen if we were to place diamond in water? Is it going to be just as sparkling? Let's figure that out. All right, so now let's figure out the critical angle for this one. All right, so M1 is going to be diamond in this case, so it's going to be 2.4 something, and water is going to be 1.33. All right, and now the critical angle is going to be 33 degrees. And the incident angle was 28 degrees. So which means that this time the light is going to escape from the material. Which means that it's going to get refracted, which means that in water, a diamond is not going to be as sparkling. That's what it means. All right, so if you got real diamond, you can experiment with it. So in air, it's going to be sparkling. In water, it's not going to be sparkling. All right, there's going to be one more discussion that I wanted to have, but let's go along with it for now. Anyway, so fiber optics, by design, they have extremely large index of refraction. Larger the index of refraction, the smaller the critical angle is, right? And the light enters into the fiber optics at an angle which is going to be much, much larger than the critical angle. So no light is going to get a chance to escape from this material. So that's what happens. All right, this is beautifully done. I love this picture. You got different mirrors, obviously, angle different. Right at the critical angle, here's what's happening. Yeah, whatever that critical angle is, you can see that the light is going this way, right? Okay, at an angle larger than the critical angle, like it's internally reflected. At an angle smaller than the critical angle, the light is going to escape from the material. Okay, so I'm gonna say something weird for you guys to remember. Shark attacks. Let's talk about the shark attacks or whatever. All right. Hopefully, it's true that the sharks would not eat people, and they do sometimes, and it's always assumed that that's a mistake. Let me tell you what the shark sees underneath. Okay, so the shark is swimming here, right? At the critical angle, they will see what's at the water surfaces. They can see it clearly, in essence. All right, as long as they can see people from other animals. If they're hunting for people, they're going to come after you, obviously. Sometimes they confuse people with sea lions or whatever. That's what they say. I don't know how true it is. These are fairly smart animals, intelligent animals, in essence. They can actually see everything all the way down to the seashore. All right? At a given angle, at the critical angle, they're going to be able to see everything at the water level. All right? If you're in a boat, they can see in a boat. They can see just clearly all the way through. All right, if the shark is hunting, they can also see the reflection of what's beneath them, underneath. Okay, so they can see the fish, schools of fish here and there. If they want to go after that, they can also go after that. Also, if they want to hunt something which is flying, they can also see that stuff. All right? Just remember, they got the upper hand. Once you're in water, you're in their territory. All right, in essence, this problem, I'm hoping that I've done this problem, the numerical, because the numbers here are kind of interesting. So we're going to be looking at things from a fish's eye, in essence. All right, so let's find the critical angle. All right, so this is going to be this angle. And then by using the critical angle, we can check to see what the fish sees at 40 degrees, 48.8 degrees, and 60 degrees. All right, so here's the index of refraction for water. This is the index of refraction for air. So we got a formula for the critical angle, so this is what we will get to use. M1 is going to be water in this case, so same with 133, and 2 is going to be air. And it's going to give us a critical angle, so this is 48.78 degrees. So at this angle, the fish is going to be able to see everything at the water surface. All right, so 48.8 degrees, the fish is going to be able to see everything at the water surface. Any angle larger, smaller than this, it's going to be able to see what's underneath or beneath. Any angle larger than that, it's going to be able to see what's above the water surface. So that's what it means. So the 40 degrees, it's going to get refracted. No, this one is going to be at 40 degrees. It's a refraction. Okay, so it's at 40 degrees. It's an angle smaller than the critical angle. It gets refracted. All right, so it's able to see what's up in there. So this is the critical angle, so it's going to be parallel to the boundary, so it's going to be able to see everything at the water surface. At 60 degrees, it's an internal reflection. So it's going to be able to see everything beneath. All right. What if, instead of real diamond, what if you have fake diamond? Can you tell the difference between the real diamond and the fake diamond? All right, both of them will be shiny and both of them will sparkle. And obviously, one of them is real cheap. The other one is real expensive for no reason at all. It's just stupid. Guys, it's diamond is diamond. It doesn't have any intrinsic value in reality. Right? For commercial reasons, we pay tons of money for it. And artistically, it's interesting, but how can you tell the difference? If you have a fake diamond, the index of refraction of fake diamond is going to be the same as corn syrup, which means that if you dip it into corn syrup, it's going to stop shining. All right, so that's what it means. Or if you put it into corn syrup,
all right, now there's
going to be an index of refraction matching.
This experiment's going to start with 2 containers, and this first container I'm going to fill up with water. Most of the way up, there we go. That's about right. And the second container I'm going to use corn oil, about the same amount. Now that we have these containers ready to go, the next step is I'm going to add an empty test tube to each one. We'll put one in the water first. We can see it, and I'm going to fill it up with water. And there it goes. And we can still see it very plainly. Now let's try one in the oil. Get one here. There it is. Put it in the oil. We can see that very plainly, but let's fill it up. And the test tube seems to disappear. Now let's see that again. Here we are in the water. Fill it up. There it is, plain as day. We can see it very easily. Let's try the oil again. While it's empty, we can see it very plainly. But once that fills up with oil, it seems to disappear. Now the answer is, it has the same index of refraction as the oil does. And that means they both bend light the same way at the same angle. So that's what's making it hard to see the test tube inside the oil. Now that you understand this concept, we're going to take this broken test tube and make the oil appear to make it whole.
All right, that was cute.
All right, now this experiment.
Okay, guys, so index of refraction matching. All right, so which means that the light doesn't bend through both materials, or more like it's going to bend the same amount through both materials. As a result, the second material becomes invisible. It's kind of neat. All right, so you have some glass material on the inside. And then whatever it is that he's going to be pouring in, index of refraction of this is going to match the index of refraction of glass on the inside. As a result, the glass on the inside is just going to vanish. It's awesome. And now you can see it right through it. It looks like a magic trick at that point. Beautifully done. So that's known as the index of refraction. All right, here's your fake diamond. I think this is corn syrup. All right, so I just place it, put it in. You get what you pay for, guys. It just vanished. All right. All right, once again, it's called index of refraction. My contribution to this is just the sound effects. Mirages. What's causing the mirages to happen? All right, so the mirages usually happen whenever there's air. All right, so what's happening within air that causes a mirage usually? All right, so look at that. All right, so what's happening to the index of refraction? Evidently, when the air is heated, the index of refraction goes down. All right, so the index of refraction is going to go down when it is heated. All right, so you got the cooler air, it's gonna be hot air. And so closer to this surface, which means that it's gonna be less dense. All right, so you're looking at the surface from a cooler environment. So you're looking at things from a dense environment into a less dense environment. So which means that if you're looking at things from an angle larger than the critical angle, you end up getting an internal reflection as a result. And the eye likes to see things, your mind likes to see things in a straight line. So the top of the car is going to look like inside the surface. So the car is going to look inverted to you. All right, so you end up experiencing total internal reflection in essence. All right, so your eyes are located at a cooler region. The surface is hotter. All right, so what that means is the light is going to be coming from a denser medium into a less dense medium. If the light hits a boundary at an angle larger than the critical angle, you end up getting an internal reflection. So which means that you're going to end up seeing the sky on the ground. It's going to look like water.
Other miracle stories may also have scientific explanations. When Jesus walked on water over the Sea of Galilee, his disciples took it as proof of Jesus' divinity.
Oh yes, the walking on water. Well, that's of course an excellent example of the inferior mirage, where one sees a hot surface that apparently reflects the sky beyond it, and you interpret this reflection of the sky as a pool of water.
Inferior mirages are low-level atmospheric phenomena that can happen over water or land. When the air just above the surface is hotter than the air a few meters higher up, the conditions are right for this confounding optical illusion. Light rays passing through the atmosphere bend with the variations of temperature, and wavering double images appear near the surface.
Everything that you see in a mirage is a distorted image of something that's really out there, caused by the fact that light rays are not taking a straight line path through the atmosphere.
The human mind may interpret these images as reflections in water, yet the pavement in this scene is actually bone dry. A superior mirage causes things to appear higher than they actually are. These ice walls, known to sailors as the Fata Morgana, are actually a reflection of the surface ice. They don't really exist.
Dispersion is breaking a light into its color components is known as dispersion. Notice that the red on top, the violet is at the bottom. So the question is why? All right, and what causes the color separation through a prism? Becomes a question, obviously. Okay, guys, you kind of know the answer at this point. I hope that you do understand the answer, right? So you kind of know the answer because, look, the violet is going to bend more through the material than red does. So what that means is that red is going to be moving faster through the material than violet will. So the question becomes, so dispersion happens because different colors will move at different speeds through the material. Different wavelengths will move at different speeds.
Refraction occurs when light enters a medium, such as glass, and bends. To make use of this phenomenon, makers of glasses, microscopes, and telescopes can grind curved lenses that focus light to a point. But before that, it's possible to see refraction in its natural state. And here's a clear-cut example. A glass prism not only bends or refracts a beam of light, it also reveals that plain white light is composed of all colors of the rainbow. This process is called dispersion.
All right, so breaking light into its color components is known as dispersion. Incident light going through our prism. Upon exiting, it's going to separate into its color components. Red is bending less, violet is bending more. Red is bending less because it's moving through the material faster than violet. All right, so the question is why? The answer is because, evidently, the larger wavelengths will travel faster than the smaller wavelengths. So the wave speed is a combination of wavelength and frequency for the reasons explained before. Frequency at the boundary is going to remain constant. So which means that the larger wavelengths will travel through the material faster. That's it. Or put differently, instead of saying larger wavelengths will travel through the material faster than the smaller wavelengths because the frequency at the boundary is constant, we will say different wavelengths will have different indices of refraction. Translated to English, that means different wavelengths will travel at different speeds through the material. All right, so red is a larger wavelength, so it's going to travel faster through the material. So which means that it's going to have an index of refraction. It's going to be smaller than the color violet, which means that the violet is going to be moving slower through the material than red. So that statement is true. I don't care what kind of glass you're using or diamond you're using. All right, so the dispersion, I see derivation now. It's more of a mathematical statement. All right, so separation of light into its color components through a prism. Okay, what do we know? The frequency at the boundary is going to be the same. Larger wavelengths will travel faster, so that's what it means. Red is a larger wavelength than blue or violet, so which means that the red is going to be moving faster. Red is going to be larger than blue or violet, so it goes through the material faster, so it's going to bend less as a result. All right, so that is the meaning of it. So the larger wavelengths will travel faster. Rainbow. All right, so let's talk about the rainbow. When you're looking at the rainbow, what do you see? Once again, on top, red is going to be on top. Let me check to see. All right, you can see it better. All right, so speaking of rainbow, red on top, the violet is going to be at the bottom. Okay, so what's kind of the color separation when you have a rainbow? All right, so the rainbow is going to happen only when there are water droplets. And then here's what happens when there are water droplets. Here is a single water droplet. All right, so the light enters into the droplet, and then it's going to experience refraction. Notice that the red is going to bend less, the violet is going to bend more as soon as it enters into this water droplet. And then if it hits the boundary at an angle larger than the critical angle, there's going to be an internal reflection. So the red is going to get internal reflected, and then it gets refracted out. The violet is going to get internal reflected and gets refracted out. All right, so now we got the color separation, nice color separation. All right, so if your eyeball is located right here. All right, this is your eyeball right here. So you're looking at this water droplet. This is your eyeball. And these are your eyelashes. All right, notice that your eyeball is going to intercept this light. You're looking up at this water droplet. You see a red here. And what's happening? You end up missing the violet completely. So you won't be able to see the violet from this one. But if there's a water droplet here, so the violet from this one is the one that your eyeball is going to catch. And the red one is the one that you're going to end up missing. All right, so from the water droplets above, your eyeball is going to intercept the red light. And the water droplets below, your eyeball is going to intercept the violet as a result. So the top of the rainbow is going to look red. The bottom of the rainbow is going to look violet as a result. All right, so that's the explanation for it. All right, so your eyeball is located here. From this water droplet, your eyeball is going to intercept red, and from this water droplet is going to intercept violet. So the top of the rainbow is going to look red, the bottom is going to look violet, and then you end up getting a color separation, obviously depending upon the refraction phenomenon that takes place. So every single rainbow is going to look the same, and you will see the same color separation in every single one of them.
One of the most celebrated atmospheric optical effects is the rainbow. When sunlight meets almost perfectly round raindrops in the atmosphere, the light is refracted or bent as it comes out. As light of different wavelengths is bent to slightly differing degrees, the color spectrum is liberated, becoming a brilliant multi-hued arc. But why is the rainbow visible only when our back is to the sun? It has to do with our position between the sun and the raindrops in the sky.
Now, there's a point in space which is exactly opposite the sun. It would be marked by the shadow of your head on the ground. I will call that the anti-solar point. The rainbow lies on a circle which is centered on the anti-solar point. And so you see that portion of the rainbow circle, which is above the horizon.
Unrestricted by the horizon, a dramatically different rainbow can be seen.
For instance, if you were in an airplane,
looking at the sun shining on a rain sheet, in principle, you could see the whole circle. Now, that's a kind of a rare thing. You have to be sitting in the pilot seat, not in the passenger seat, to be able to see that wide angle. But in theory, the rainbow can be a complete circle.
Astronomer Andrew Young of San Diego State University says that rainbows are a totally personal experience.
No two people ever see the same rainbow because one person standing here sees the raindrops that are over here, and the other person standing here sees the raindrops that are over here, and all these raindrops are illuminated by the same sun, but there's this fixed angular deviation of the sunlight, so each person sees a different set of raindrops illuminated by the sun.
All right, let's finish this up. Why is the sky blue? It's kind of weird because every single person probably asked this question at some point. Especially this is a question that a lot of kids usually ask. And then eventually you kind of give up on the question regardless because you ask adults and most adults wouldn't know. And today you can Google it. And then when you Google it, what happens? It's going to take you to Wikipedia and then there's going to be an explanation that you won't be able to follow. It's weird. Anyway, so I was on a date with this girl when I was a senior. And the first question that she asked is, oh, so you're a physics student, right? I said, yeah. She said, so I was always wondering, why is the sky blue? She never came up with, she never had a good explanation for it. And then I'm thinking, oh, that's a good question. I don't know the answer, obviously, because in none of the physics courses that I took, we've ever done physics the way I do physics. It's usually derivation after derivation. You become really good at math, per se, but you don't really understand physics too well. Right? It's until you start teaching physics at an art school or something, because no one ever discusses physics. You would talk about the Snell's law, and then you probably solve, God knows, gazillion problems with it, and you still have zero understanding of what's going on. This is how traditionally physics is being taught. And then I'm thinking, oh, I had the same question before I got into physics, obviously, but I don't know the answer, and I don't want to embarrass myself saying, yeah, I don't know. I mean, it's a simple question. I should know the answer. So I'm trying to impress her. So I said, oh, the sky is blue because the ocean's up. You know, the light gets reflected back to the sky. And then she was perfectly satisfied with that answer. Okay, and so glad that she didn't ask, well, if that's the case, why is the ocean star blue? I would have said, because the light gets reflected from the sky as well. All right, completely made up. What's the real reason for it? A lot of you guys mistakenly think that that's refraction. All right, because the sky, the atmosphere refracts light, which is correct. If it's refraction, guys, at the bottom of the refraction happens, obviously there's going to be dispersion. So the largest angle is going to be violet. If refraction and dispersion was responsible for it, the sky would be violet. So that's not a real explanation either. A lot of people mistakenly think that that's the reason why. Okay, so the sky would be violet if dispersion or refraction was responsible for it. All right, so here's the explanation for it. I don't know, when this picture got digitized, a lot of colors got mixed up, but at least in the middle, you got the white. All right, so the sun is actually white, it's not yellow. All right, if you're looking at the sun through the vacuum of space, if you're out in space, if you're looking at the sun directly, it will look white because it's this. If you combine all the colors into a single color, everything is going to look white. That's the meaning. The reason why the sun looks yellow, because what happens is the blue light gets diffracted from it, and what's causing this diffraction is called scattering. All right, so the sky is going to look blue to us because the blue light gets scattered more than any other color going through the atmosphere. So which means that the molecules making up the atmosphere will scatter blue light more than any other color. So the question is, what is scattering? I don't like this explanation that much. Let's skip this one. Where's my explanation?
The sun gives off white light. Why is the sky blue? We posed the question to Robert Greenler, professor of physics at the University of Wisconsin in Milwaukee.
We ought to start with is not why is the sky blue, but why is the sky bright? For instance, the sun is up there, and you look in that direction and see brightness in the sky, it means there's light coming from that direction to your eye. Now, how does that happen if the sun's over there? And the answer is scattering.
Light waves, like the water waves in this pond, are scattered by obstacles in their path, sending wavelets off into new directions. Air molecules are just large enough to scatter the light coming from the sun, sending it off in all directions. But why is it blue?
The answer is that when you get light scattered off particles, in this case molecules, that are small compared to the wavelength of light waves, you tend to scatter the blue end of the spectrum more than the red end.
White light is made up of light waves containing all the colors of the spectrum. When these light waves hit air molecules in the atmosphere, the blue portion of the spectrum is then scattered or deflected toward the eye.
Okay, so the light gets scattered. Okay, once again, explanation, I like his explanation, but the explanation that I prefer is, I don't have that. All right, guys, the absorption and remission of light by the atomic electrons. So they absorb the light, they become energized. And then when they're energized, they jump up to the next energy level. They will stay there for a fraction of a second. Upon jumping down, they will release the light. Right? So which means that they will remit the light at a random direction. For whatever the reason that we will have to investigate, the atoms and molecules making up the atmosphere have a preference for blue light, meaning that they have a preference to absorb and remit blue light more than any other color. So the question is why? All right, so that's something that we will get to investigate.
As the sun sets into a crystal,
So let's get out of here.
as the sun sets into a crystal clear twilight, one of the most mysterious types of mirage may appear. A spot of green that briefly and unexpectedly comes into view at the tops of the red sphere, or perhaps hovers for a second or two as the sun dips out of sight below the horizon. Jules Verne wrote of the green flash that one who witnessed the flash would be able to see into the hearts of others.
What happens is that the atmospheric refraction, which is responsible for mirages and other phenomena, is quite considerable at the horizon. It actually is enough to raise the sun at the horizon by its own diameter. But that raising of the image is not equal for all colors of light. For the shorter wavelengths, like green and blue, the image is raised up a little bit more.
But the blue light waves are scattered by the air molecules, leaving a rare last glimpse of green, something extraordinary enough to be taken as an evil omen by sailors throughout the millennia. Every day and night, there are bedazzling lights and colors in the sky. We see these effects and are intrigued. But what do we see? Is it really there, or is it an illusion? Thousands of years ago, our ancestors saw gods and angels in the light show in the sky. Wars were launched, famines predicted, and people inspired or paralyzed with fear by their interpretations of heavenly events. Today, we see the same effects, and with scientific understanding, we can have a different appreciation. All around, there is beauty and magic, a spectacular light show open daily. To enjoy it, you need no special equipment, no special training. Just keep watching the skies.